Hello everybody, I'm Ahmed Al Hassan. I study at University of Khartoum. This year a finalist in electrical and electronic engineering bachelor's degree. I welcome you to this tutorial about multiple linear regression and polynomial regression. As you have been taught in this brief lecture, multiple regression uses points of data that have multiple features to predict um, uh, values or a class of data. For example, um, suppose that we want to predict the housing price or a price of a house using maybe number of rooms, size of this house, um, number of uh, kitchens maybe in this house, and so on. Using these multiple features, we can fit this data in a multiple linear regression model. In this case, we have three features. So we will have the bias and other three weights to uh, for the model to fit. And for the polynomial regression model, suppose that we are working in maybe a lab and we have some points in a maybe 2D plot. Let's call them X and Y, and we have to find the relation between X and Y. And we think that maybe a polynomial equation may fit um, to a very good extent for this for this data. We might try multiple polynomial regression models. In this is for the polynomial regression model, we assume that y may equal some polynomial equation of x. We have y equal to bias plus weight by x to the power 1 x plus weight by x to power 2 and so on, and some weight multiplied by x to the power n. Um, we, in this tutorial, learn how to structure the inputs for relation using the design matrix, which is the features matrix. Generalize the MSE for multiple features using the orders where least squares estimator. Visualize data and model fit in multiple dimensions, fit for regression models of different complexities, plot and evaluate the polynomial regression fits. As I said in polynomial regression model, we might try multiple models depending of the final power we have. Maybe we stop at power 5 or 7 as um, um, we start by looking at this video of multiple linear regression and polynomial regression. Um, then the video is available at YouTube. You can see it anytime you want. We have to do some setups, importing NumPy and Matplotlib to PyPlot as PLT to plot our data and the models that we made. These are some figure settings. You can double click to see style of it and configuration. And the last thing to of setting up this tutorial is some helper function that plots fitted polynomials, which we make a polynomial model, and then we draw the equation of it. First of all, we have multiple linear regression. We have this equation of the multiple regression that this target y target is equal to x multiplied by theta, and there is some error to our model. So this is the model, our model, and this is the error, and this is the target we are trying to predict. We have to minimize this error as much as possible. This equation in the matrix formula, matrix form, and X is called, or sometimes referred to as, design matrix. First, we will simulate some data, and as you can see, it's two features, and is a target. And to generate the optimal parameters, or also called ordinary least squares parameters, to make the ordinary least squares estimator. This is the one we use for single regressor, and it holds true for multiple feature regressor. And instead of using this scalar version of it, we will use some matrix version of this equation. We will implement this equation and in this cell. First of all, we will remove this raised exception. And then we will write the equation of theta hat, or theta optimal. We have this inverse. So it would be numpy dot linear algebra dot inverse for x dot transpose multiplied by, and this is a matrix multiplication, x, which all of them are multiplied by, yet again, an x transpose, and the end we multiply by y target. We return this theta hat. We will print them and comment these two lines and see our results. As we can see, those are the same, so our solution is correct. Then we can obtain our mean square error for this set of parameters. We run the cell, and we have a mean square error of 91.91. We will execute this cell to visualize the predicted plane. We have this plane, and we have the original points, the original data points. This plane represents the model, and there is some difference, as you can see, between those points and the point predicted by the plane. And then we go to polynomial regression. As you can see, it predicts that y is an equation of some polynomial of x. In this case, is up to power 3 of the third degree. This is the special case of single linear regression using a single feature. We can make it as we can make as big bar as we can. So we can generate multiple polynomial models and compare them to choose the best one or the more general one. Note that the more features we generate, the more it gets overfitted, and we want a general model, and not a model that fits perfectly to our data and give us maybe some unwanted results. Um, First, we will execute to simulate some data. We simulate this data according to this equation, and we add some noise to the input and output to the x and the y. So this equation may be fitted pretty much by making a degree of the second, an equation of the second degree. Then we will make design matrix, or feature matrix. We remove this exception. We then make design matrix, which is we can do by np dot horizontal stack of the design matrix and x raised to our degree. So this design matrix will be from 1. We first make ones, and then we add x to the for 1, and x to the 2, x to the 3, x to the 4th, x to the 5th, and so on. Then we uncomment these two to compare our results with the one printed here. And as you can see, those are the same, and we have to fit the models, our model now. Now we will use this function solve for regression. We're using the ordinary squares function. First, we have to make our design matrix, which make design matrix by passing the x and the order we want to make our polynomial function, and then we will make this this theta by ordinary least square, by generating all the least squares of it, using the x design we generated and the targets we have, and then we will plot these models. I forgot to remove the exception, and then we will try it and see the results. We see that for both of them, that our results matches the one printed here, the one plotted here. And then we will compute the mean square error as a exercise. And you have this plot to compare your solution to it. In summary, we have seen the linear regression model, and we can compute the optimal parameters for it, and we saw also the polynomial models. And as I said, that the higher the order, the more fitted the data is, and the less mean square error it have. But be aware that maybe you can reach the point of overfitting, which is not good for your models. Thank you.